So this video is going to be a continuation of our discussion on crystal field theory. So in the last video we talked about how in these octahedral compounds the energies of the d orbitals can be split off, and for some ions that you can have two different electron configurations, low spin versus high spin. So how do you know if a compound is going to be high spin or low spin? It all depends upon which is the lowest energy state. So let's work an example here. Let's explain why the ferrocyanide ion is a low spin ion if the field splitting is 33,000 per centimeter. And we'll talk about that unit in a minute. And the pairing energy is 17,600 per centimeter. So what we're really going to do is calculate the energy of the formation for these two ions, the crystal field stabilization energy. So we said in the previous video, we said for a D6 ion, for a high spin D6 ion, the crystal field stabilization energy comes out to be 2/5 times the field splitting. So we're going to multiply, and it's negative because this is energy that we get out. So it's negative 2/5 times the field splitting, or negative 2/5 times 33,000, which comes out to be negative 13,200 per centimeter. Okay. So now let's do it for the low spin case. For the crystal field stabilization energy for the low spin case, we calculated to be negative 12/5 delta O plus two pairing energies. So it's always a trade-off. So this number is going to be much bigger because it's 12/5 instead of 2/5, because we're putting all the electrons into the lower energy T2G orbitals, but we have to supply pairing energy. So we're going to take minus 12/5 times 33,000 plus 2 times 17,600. The 17,600 was the pairing energy. This comes out to be negative 79,200 plus 32,500, or minus 46,700 per centimeter. So the formation of a low spin ion is, in fact, more energetically favorable. Okay, we do have to supply the two pairing energies, but that's outweighed by the fact that we're putting all the electrons into one of the lower energy T2G orbitals. So what's this unit 1 over centimeters, which is the same thing as centimeters to the minus 1 power? Okay, that's a wave number. It's basically 1 over the wavelength in units of centimeters. So 1 over centimeters, or centimeters to the minus 1 power. This has the benefit that it's directly related to the energy. You see, energy is inversely related to wavelength, but if we take 1 over the wavelength, then we have a unit that's directly related to the energy. So in other words, as the wave number goes up, the energy goes up. In this case, what we'll be talking about is the field splitting. So as the number gets bigger, the field splitting gets bigger. So let's work a quick example here. So let's say the field splitting for this hexamine cobalt 3 is 23,000 per centimeter. Let's find the associated energy. Alright, so let's first convert this into a wavelength instead of 1 over a wavelength. So we'll say 1 over 23,000 per centimeter comes out to be 4.34 times 10 to the minus 5th centimeters, which is 4.34 to the minus 7th meters, and if we multiply 10 to the 9th, that converts it into nanometers, and that's 434 nanometers. So you might remember that the visible spectrum falls from 400 to 750, right? So this does in fact fall. Remember I said that the splitting, well anyway, we'll get to that, but the splitting off of the orbitals falls in the visible region of the spectrum. So 434 does fall within the visible region of the spectrum, barely. So if we're going to calculate the energy, corresponding energy, E is equal to hc over lambda, which is 6.63 times 10 to the minus 34 the joule seconds, times 3 times 10 to the 8 meters per second, divided by the 4.34 to the minus 7 meters, and meters will cancel, seconds will cancel. This gives us joules. That's 4.58 times 10 to the minus 19th joules. So when we started out talking about transition metal compounds, one of the things that we said we wanted to be able to explain is why are all these transition metal compounds colored, okay? And we talked about how the energies of the orbitals in an octahedral set of ligands, the energies get split off, the energies of the orbitals get split off into the T, 2G, and EG sets. Well, for many of these complexes, this field splitting falls within the visible region of the electromagnetic spectrum, right? Just like that last calculation with the cobalt hexamine, the field splitting corresponds to a wavelength of 434 nanometers. That falls in the visible region. So why are these compounds colored? So as white light, and you might recall that white light is a combination of all colors. As the white light passes through a solution, so if the solution appears colored, certain wavelengths are going to be subtracted from the spectrum. What happens is the energy gets absorbed, and it's used to promote an electron from T to G. We'll go to the simplest case, just one electron. It's used to promote an electron from the low energy T2G to the higher energy EG. All right, so you have this white light coming in. You remember white light is a combination of all colors. It has a red component, a yellow or orange component, it has a green component, a blue component, a violet component, even though I didn't show it. So let's say that this field splitting corresponds to green light. Okay, so what happens is that white light passes through, the green light gets absorbed. The green light gets absorbed by the compound, and the energy is used to promote an electron from this T2G to the EG. So after the light passes through, the green component is missing. The green component has been absorbed by the solution. Okay, now usually these absorptions tend to be very broad, and it's not just a single wavelength that's absorbed. So anyway, so does this mean that the solution appears green? No. The color that's observed is the complementary color to the color that is absorbed. So we can get a rough idea of complementary colors by basically arranging them in a color wheel and going around the spectrum, or going around arranging them in a circle, red, orange, yellow, green, blue, violet, okay, from 750 down to 400. That's the visible region. So two colors are complementary if they lie opposite one another on this color wheel. I mean, this is a crude approximation, but two colors lie opposite one another, or complementary if they lie opposite one another on this wheel. So For example, orange and blue are complementary. Okay? So that means then, right, opposite one another. Orange here and blue here. So that means then that a solution, as absorbs blue, appears orange. And a solution which absorbs orange appears blue. For a minute, let's go back to this example that I used, the cobalt with the 6 ammonias on it, the hexamine cobalt 3. That ion is orange in color, very, very undoubtedly orange in color. And you look at where the field splitting corresponds to a wavelength of 434 nanometers, which is in the blue region of the spectrum. So it appears orange and is absorbing blue. Okay? Same thing for red and green. Red and green are complementary. Red and green are opposite one another. So your solution appears red, is absorbing green, and vice versa. And yellow and violet are complementary colors. So if solution appears yellow, it's absorbing violet, and vice versa. Alright, so blue and orange, red and green, and yellow and violet. Now you have to understand too that a compound appears colored only if it absorbs in the visible region of the spectrum. If it's not absorbing anything in the visible, it's not going to be colored. Sometimes you do have, like I said, these absorptions can be broad. And sometimes you might have an absorption that's, let's say, centered in the ultraviolet, and you just have a portion of it falling into the violet region of the spectrum. Compounds like that tend to be pale yellow in color. In other words, if the field splitting becomes so big that you've shifted the absorption into the ultraviolet, if you have just a tail of it going into the violet, it might be pale yellow in color. Anyway, so what we call the spectrochemical series ranks the ligands from those producing a small field splitting to those which produce a big field splitting, right? So here's our spectrochemical series. Alright, so we're going from small field splitting to bigger and bigger and bigger field splittings. Okay? So down here, and note the way these are kind of grouped. So here we have the halide ions, iodide, chloride, fluoride. Then we have some oxygen donor, oxygen-sulfur donor ligands like hydroxide, water, thiocyanate ion. And then what do these have in common? These are all nitrogen donor ligands, ammonia, EN, which is the abbreviation for ethylene diamine, and nitrite. And then on the very end we have cyanide and carbon monoxide, which both produce very big field splittings. There's a reason for that, and that the cyanide and carbon monoxide, when they bind the metals, they typically form very, very strong bonds. That's sort of another topic of discussion. So we can make some qualitative comparisons here. We can make some qualitative comparisons about these spectrochemical series. For example, let's look at these two compounds. Okay. Let's say we have, and this is an example that I've used previously, when you dissolve nickel salts up in water, it forms the hexaalkyl ion that's green. If you add 15 molar ammonia, it changes to a violet in color. So the hexaalkyl is green, the hexaamine is violet. So the question I'm going to ask is, okay, does this support the spectrochemical series? Well, if you look at your complementary colors, a solution that appears green is absorbing red, okay, and a solution that's violet is absorbing yellow. So the question then you have to ask yourself is, right, absorption occurs when the energy of the incoming light matches the field splitting. So in other words, here's red is being absorbed and here yellow is being absorbed. So which is the higher energy light? Photons of red light or photons of yellow light? So you remember the way your color spectrum goes from red, orange, yellow, green, blue, violet, right? If you go red, orange, yellow, green, blue, violet, that's going to shorter wavelength. It's also going to higher energy. So yellow is higher energy light than red light, and that means then the field splitting is bigger here than it is here. Okay, which supports the spectrochemical series, or because ammonia lies ahead of water in the spectrochemical series. Okay, we could also compare, for example, tetrachlorocobaltate versus tetrathiocyanatocobaltate. The tetrachlorocobaltate is blue, very intensely blue, which basically means it's absorbing in the orange region of the spectrum. And the tetrathiocyanato is violet, which complementary to violet is yellow, means it's absorbing in the yellow. So you'll have to ask yourself the question, which is higher energy light, orange or yellow? If your spectrum goes red, orange, yellow, green, blue, violet. Yellow has a shorter wavelength, therefore higher energy, right? So higher energy light is being absorbed here than here. And if you look at your spectrochemical series, thiocyanate lies considerably further ahead of chloride. Now, some simple qualitative comparisons will work like this only if you're dealing with the same metal with the same charge with the same number of ligands on them, right? So both of these are nickel 2, and both have 6 ligands on them. So we can say something about the field strength of ammonia versus water, but we couldn't make a comparison. Let's say comparing a chromium to a nickel. We can't compare apples to oranges. We can only compare apples to apples. So the same metal with the same number of ligands and the same oxidation state. Same thing here. Both of these are cobalt-2 compounds, and both of them are tetrahedral compounds. And both of them have 2- charges on them. Alright, so remember that as science goes, you can only change one variable at a time. Here, the only variable that we're changing is the number of, is the type of ligand. The metal's the same, the charge is the same, the number of ligands is the same. So, last thing here. Alright, so we said that these transition metal compounds are colored because we're splitting off the energies of the d orbitals, and the energy of that splitting falls in the visible region of the spectrum. They're absorbing visible light, that's why they're colored. Those DD transitions are subject to some quantum mechanical selection rules that we need to talk about. Alright, so the DD transitions and these transition metal complexes are governed by these selection rules. Alright, so first of all, it says that electronic transitions are forbidden in a molecule that has a center of symmetry. Okay, and octahedron has a center of symmetry. A tetrahedron does not. So technically, those DD transitions that give rise to these colors are forbidden in an octahedral compound, and not forbidden in a tetrahedral. So the tetrahedral compounds tend to be more intensely colored. If you look at, so what do we mean when we say it has a center of symmetry? If you look at an octahedron, okay, everything has an opposite through the center, right? So this point is opposite that point, okay, and that point is opposite that point, and this point is opposite this point. Everything has an opposite through the center. That is center of symmetry. A tetrahedron doesn't have this. So if we look at a tetrahedron, you can think of a tetrahedron as being inscribed in opposite corners of a cube, like this. Okay, and now every point does not have an opposite through the center. Alright, so if this point we're going to have an opposite through the center, it would come down and there'd be another atom or ligand here, and we don't have that here. So this has a center of symmetry, this does not. So one more time, octahedron has a center of symmetry, a tetrahedron does not. Okay, and that makes these DD transitions forbidden. So you might want to say, okay, well, why are they colored at all? Why are so many octahedral compounds colored? Because no complex has perfect symmetry. You have molecular vibrations and so forth taking place that relax the symmetry. But nonetheless, tetrahedral compounds tend to be more intensely colored. Okay? Second rule is that electronic transitions cannot change the spin state of an electron. Alright? And this typically comes into play when you have high spin D5 ions. Okay, they tend to have tend to be very pale in color. So, for example, some manganese 2 compounds, some iron 3 compounds, colors are very pale. Manganese acetate is pale pink in color. The color is so pale, even in a solid, that you would have to hold it against a white background to tell that it's colored at all. Okay, and so as a consequence then of that D5 configuration, right? So if we split off our orbitals, right, into the T2Gs and the EGs. Now, if we only have five electrons, and we have a high spin D5, we're going to go 1, 2, 3, 4, and 5. Well, now we have a problem. We have a problem because if we go to promote an electron, we're going to have to change the spin state, and we're going to have to pair them up. So we'd have to add, there'd be some sort of, in addition to the promotion of the electron from here to here, there would also be some sort of penalty associated with having to pair up the electrons. Alright, so the quantum mechanical rule says that can't happen. We'd have to change flip the spin state of the electron if we were going to pair them up. Okay. Now, third rule is, and this is the last thing, that no electron transitions can occur in D10 ions, right? So this is one of the other things that we said we wanted to explain when we started talking about crystal field theory. We said so many of these transition metal compounds are colored with the exception of zinc. What's the problem with zinc? Why are all the zinc compounds white or colorless? Because zinc is a D10 ion. You cannot have DD transitions when all your orbitals are completely filled. There's no way to promote an electron. So say we have a D10 ion, we'd have to add 5 more electrons. So now all the orbitals are filled. If we promote an electron, we'd be trying to put 3 electrons in one orbital, and that's obviously is not going to happen. So you cannot have transitions at all. Okay, no transitions are possible, not even a little bit. So zinc compounds are not even a little bit colored. completely colorless or white. So electronic transitions are forbidden, and the molecule has a center of symmetry, which an octahedron does, tetrahedron does not. So tetrahedral compounds are more colored, more intensely colored. We can't change the spin state of an electron, meaning we can't promote an electron and pair them up, okay? And we can't have electron transitions in D10 ions, okay? So now having covered something on coordination chemistry and crystal field theory, we can go in and talk about the chemistries of some of the transition metals.